Okay, now I assume you guys can see this right here, the slides here. Sorry about that, I was muted. So now let's start over again here. So I'm going to just, if there's any questions, put them in the chat, and I'll just go on here then. Okay, so today we're covering normalization theory, and let me just go over the quick introduction I did last time, just so that we can kind of refresh here what we're talking about. So the central notion in normalization theory is this idea of a functional dependency. So here's like a table, and here is a functional dependency that holds over the table. So if you have the person ID, then you can functionally determine the name, the street, and the city. So formally what this means, if two tuples from the relation have the same PID, then they'll have the same name, street, and city. In this case, then it would be basically, there are no two tuples of these things, but if there was under set semantics at least, another tuple with PID 20, then it had better have Mike and this address here, and then Umio as the city. This is a better example here because this will actually have two tuples of this that have this. Street and city determine the postal code. So this street address in Stockholm and this street address in Stockholm determine that postal code. So any two tuples that share the same street and city also share the same postal code. And these few things you could say in the world or whatever, these always hold. So there can be no exceptions to these functional dependency rules. They just are the way things work in the domain. I know that somebody is not muted, so just check to make sure that you're muted. I can go here and I hear somebody's background, so please mute if you're not. If your speaker's on or if your microphone is on, I'm sorry. Okay, so yeah, I think I'm actually gonna go in and actually do it. So I need to get the participants. Okay, so I'll just fix that. Yeah, I muted them. Okay. So so if we recall here, then what we show here is we show that if you just have what's called the universal relation, so kind of a naive way of doing database modeling is just to take all the attributes and put them in one giant like spreadsheet, if you will. And what happens when you do that is you get a lot of repeated kind of redundant information. So that leads to update anomalies. So the fact that if you go in and change it somewhere, then you have to change it everywhere. And then there's issues also of the necessity of extra null padding. So if we delete this Susie, well, if we can't delete a full tuple because we'll lose information, so we have to pad with nulls instead. Anyways, all of this would basically involve very complicated, expensive protocols to maintain the integrity. All right, now look, let's consider this universal relation we had here. This with 1, 2, 3, 4, 5, 6, 7 attributes here. Let's consider what would happen if we went and we did this instead. If we actually broke it into 3 different tables. So we have a table that essentially represents the account number with how who owns the account and how much money they have in the account, and then we have the table of like the customers and their addresses, right? So we have like the different addresses for the customers, and then we actually even have a third table here which associates addresses with postal codes, right? So if we did this, if we actually took that, if instead of it representing things this way here, like with this giant big table here, we represented things instead with these 3 tables here. So if we did that, so the argument here, of course, is going to be that it's somehow desirable for us to do that, for us to bust the thing into 3 tables, right? And that's what we have a good theory that guides us in doing that, and that's what normalization theory is all about. Is basically saying what is a good decomposition, and decomposition just means you're pulling things apart. Was it a good decomposition of what's called this universal relation, or this thing that just has all the attributes, the big spreadsheet, if you will. So the first question, of course, is that once we do that, do we lose anything? So I mean, when you take something apart, if you take apart, like, so, say, oh, this machine works, I take it apart, and then and then when you try to put it back together, then there's like one little screw left that doesn't seem to fit somewhere. That's kind of bad. So the question here might be that we decompose this universal relation. We decompose this into those three tables, but can we put them back together again to get back our original universal relation? And we can verify here that yes, we can. So if we do natural joins here, like call R prime is going to be R1, this one here, natural join with this one. So the natural join here, of course, here now is going to be on PID, right? So just a natural join. That winds up giving us this. And then if we do yet another natural join, where this natural join here is going to be on both the attributes. I'm sorry, one second. I actually do need to take this. This is my kid's school. I'll just be very, very quickly here. Hello? Okay, yes, sorry about that. Yeah, anyways, that's live. Okay. So what we have, what we have here is we have this decomposition is indeed lossless. So we're not losing any information in this decomposition. And there's actually a theory that guides that as well, as to why ultimately why this decomposition does not lose information. But that's one of the critical things, of course. That is, if you're going to if you're going to decompose a universal relation into some subrelations, then they always have to be what's called lossless. So it makes no sense. So if we take another example, let's say that, for instance, we did the following. We instead of, this is kind of a very naive example here, but let's say that the way we divide this is we used to say that we're going to have city and P code. That's going to be in one of the tables, and then we're going to have the rest of these things in the other table. The account, that's the amount, the owner, the name, and the street, but then we're going to completely separate the city. So when we do a natural join between those, we'll actually get a Cartesian product. So what will happen is that when we bring back and rebuild the universal relation, it's much larger. So a lot of spurious tuples are let in by natural join. No, it's not an industry standard to join natural join. Natural join, I'm sorry, that's okay. In lab 1, we're supposed to avoid the natural join. Well, I mean, doing natural joins is always risky because if the attributes don't line up, then you'll get the Cartesian product. Yeah, this is wrong, but exactly, that is a correct question. This was just an example of the fact that this is an illegal tuple at the bottom there. So this is the original universal relation. I mean, the thing is that we're doing theory today, so we're not really thinking about what industry standards are, etc. It's not really kind of how that's not really the consideration. Okay, let's just go back here. Let's look at, so we look at these decompositions. So why is this a good decomposition? This right here, this is a good decomposition. There are countless other ones that are bad because they're lossy. All right, this one is lossless because if you do a natural join of decomposition, you get back the original table that you decomposed. So decompose, you can see that as splitting up into separate tables. And if you do that, then when you actually rejoin it, when you rebuild the table from what you split it up from, you better get back the same result. That would be what's called lossless. And lossy are almost always to be rejected. There's no real practical reason why you would ever want to have a lossy decomposition. Okay, so so these are there kind of some special terms here that you kind of have to get used to. The issue of what a decomposition is and what it means for it to be lossless and lossy. Lossy is the opposite of lossless. All right, so this right here, this is a good decomposition because it helps us with all of our weird anomalies we had before. So for instance, it's less redundant. So there's only one place to change Mike's address here. So if you want to change his address, you can go into this table here and make the change in one spot. So we no longer have it so that we have to have a complicated way to update that address. So once that address is updated, it's kind of true for the whole database. We can also delete account number 2 without deleting any information about Sam. So we can wind up deleting account number 2, but we still retain Sam's information if he wants to open another account. And we can also add information on Susie without having to give her an account. So we've already, right there, we've already dealt with this this update, deletion, and insert anomaly. So that's very good. Now, does it preserve all the functional dependencies? So we originally had these functional dependencies that governed the big table, and that was that the person ID determined the name, street, and city. The account determines how much is in the account and who owns it, and the street and city determine the postal code. And as you can see here, each of the little tables, each of the tables here that it was busted up into, each of these functional dependencies live in one of those tables. Okay, so and they don't live in any other tables. They just live in that particular table. So they can be enforced over those tables here. So what we're doing is we're basically preserving the functional dependencies that we had. They're being preserved in this decomposition. Okay, so they're still each of these functional dependencies has a happy home, as it were, in one of the tables. And therefore it can express itself. So, moreover, if you look here, the left-hand side of each of these functional dependencies winds up being a primary key or a key of the little subtable. All right, and what that means, that's even better. What that means is that it's very easy to enforce these just by declaring primary keys. Okay, so this is really a nice form. All right, so this form happens to be something called Boyce-Codd normal form. So boy, can't we agree each relation is in a nice form, B, C, and F, but it actually stands for Boyce-Codd, two people, normal form. Okay, so this is actually this is what we're actually after. We're after doing decompositions that are in what's called Boyce-Codd normal form. Okay, so let's just recap here. And what I'm going to do is I'm going to do a lot of work on the paper later so that we can kind of build up some more intuition about this. But so not all compositions are so nice. So many are lossy. Various anomalies may persist. Many do not preserve the original dependencies, and they may be inefficient to maintain integrity. But this BCNF is actually good on all these. It's lossless. It gets rid of those anomalies we had. It can preserve the original dependencies, and it's efficient to maintain. So what we have a theory now that's going to guide us, and we're going to develop that theory that's going to guide us toward the proper decomposition. So this is kind of how it works. Relations, the whole relational model makes what's called the first normal form assumption. So first normal form is that basically all the attributes, all the values in the table are atomic. Okay, so they're not lists, they're not sets, they're just single atoms. This is like the first assumption always of relational databases. Then what we're going to have is there's like second normal form, which isn't really that important. Third normal form, there's first normal form, and there's something making second normal form, which is kind of for historical reasons. There's third normal form, and then there's B, C, and F. So what we want to do is we want to take our original R, and R here is just like the big table, like the big spreadsheet. And we want to drive that to a decomposition that respects B, C, and F. That's kind of what we're looking at. This is, it's an old theory, but it's still true. Okay, so the definition of B, C, and F, I think that maybe what I'm going to do is I'm just going to go through these quickly, and then we're going to actually work this on paper so that we can kind of get a little bit better kind of feeling for this. Because a lot of this is very intuitive once you kind of see it, but you kind of have to kind of play around a little bit to get to a point where you can get that intuition. But let's just finish up these slides here, because these slides are kind of a nice kind of synopsis and motivation. But later we're going to develop a bit more skill around actually working with these functional dependencies. So a relation R is in B, C, and F if every non-trivial functional dependency x goes to y over R, x is a superkey of R. Okay, and so we're going to give definitions here later of what it means for something to be a superkey and for something to be non-trivial. Okay. A superkey is just a superset of the key, and then we're going to get into like a real, kind of more rigorous feel for what that is. X goes to y as a functional dependency is trivial if y is simply a subset of x. So for instance, this functional dependency, if you have whatever's on the left-hand side of the functional dependency, if what's on the right-hand side is just a subset of that, then that's just a triviality. Those always hold no matter what. Those are always true. But the relations are, so the definition for Boyce-Codd form is simply that for every functional dependency that holds over R, that the left-hand side is a superkey of R. That's what and then for every non-trivial one that is. That's the definition here. And as we can tell that the as we can tell here, the BC and F holds here, because these are all the functional dependencies that hold over each of the tables. And for each case, the left-hand side is a superkey because it's a key of that relation. Okay, so what we're going to do is we're going to get into the real kind of let's see here. I don't know if I want to do that quite yet. I want to do instead right now. I want to go to now. I want to for us to work some stuff on paper so we get a little bit better idea of a little bit better feel for this. So let me switch to the camera here. One sec. Okay, so camera here, and let me just on the other side here, just to keep myself organized here, I want to one sec. On the other side here, I want to just have the slides that are being presented today. So I'm going to kind of go along with those, but I'm going to present them on paper here. This is going to be a little bit. I think it'll be a little more intuitive method. Okay, 1 second. Yeah. Okay. Here we go. And all right, good. Okay, so number one, this is kind of usually the way we're going to present stuff. We're going to have R. This is usually our universal relation, and we're going to have something like this. We're going to have A, B, C, D, E, and let's say F. Okay, and I think that let's see. I mean, if we look at that example we had before, we're going to basically write something like this. We're going to write like DE functionally determines F, and let's just say that A functionally determines B, C, and D. right? So what does this mean here? What this means is it means that any two tuples that agree on both D and E have to agree on F, right? Any two tuples that agree on A have to agree on B, C, and D. All right. Now, the general. So this is just a notation thing. So what we're doing the abstract examples here. So we're not going to actually write out the names of the attributes. This can fit like probably fits the example we had before in some sense. So the issue would be something like I mean, the first thing to say is that we have like a set here, and then usually what I'll do is I'll write that as some kind of script F. So that'll basically be something like this is the set of functional dependencies that we have that are governing this relation. So we always come up with this universe relation, and then we do a whole bunch of work, and then what plops out is like the decomposition. Okay, so the work that, let's see, I guess that's probably not so nice in terms of the. Okay, this probably looks a little better. Now, when we talk about a functional dependency in the abstract, we talk about something like this: X goes to Y, and so these are going to wind up being sets of attributes, right? They're not lists of attributes because if you have AA, then that's just equal to A. So it's a set. Set of attributes functionally determines another set. Now, if I say something, so we have our set of functional dependencies here, and then included always within these set of functional dependencies are all the trivial ones. So let's give an example of a trivial one. That would be like, an example of a trivial one is A determines A, let's see, BA determines A, right? So that's trivial. So if I take two attributes that have the same value for B and A, then they're going to have the same value for A. Well, that's always the case, right? That's why they call it trivial. That's why this is a trivial one. And typically we don't write down the trivial ones. They just exist as just something that's true. Okay, that's just a fact. All right. So anyways, we have this set of functional dependencies here. And what you're going to see later is we're going to talk about something called, and I'm not going to do the full closure here, but we're going to talk about something called the closure of a set of functional dependencies, which is denoted with a plus on it. And that equals a set that is much larger than this. So if we take this original set F, and then we say, let's write down all of the non-trivial functional dependencies that flow from these, then that becomes, then of course, the E comes from that, and A goes to B, C, D come from that. But then also what comes from that is that we have what's called a splitting rule, okay? And the splitting rule would basically say that if A goes to B, C, D, that also means that A goes to B, A goes to C, and A goes to D. As well as A goes to B, C, A goes to B, D, A goes to C. There's a whole bunch of them that would come from that, right? So that's kind of that's what you would call a splitting rule. So basically, what it says that if X is a set here, X is a set here and Y is a set here, then you can actually wind up having a whole set of functional dependencies that follow from this, where you just pluck off subsets of Y. All right. So if X goes to Y, then X also goes, determines some subset of Y. Right? And that's kind of what's expressed here. Does that make sense? Paper's too bright and a bit hard to read. Yeah. I'll darken it down here. Maybe will that make it better? Is that better now? I hope. Good. Okay. Yeah, close myself in here. All right, but I mean, I hope that people yes, they do need to be unique. So when we're talking about these are all unique. They don't equal one another. Okay, good. All right. So this of course there's a lot more to go here. So we haven't finished here. We haven't finished kind of grinding out all the functional dependencies that flow from a given set. So usually this given set is something that we can kind of elicit from people. Like we might say something like for instance, like an example might be, this is kind of a really trivial example. If I say that A is like an object ID, B is the X coordinate, this is the Y coordinate, this is the Z coordinate, and this is the time. Okay. So then it might be like if I said something like this, if I say at a particular, only one object can occupy a certain position in space-time, that's like saying B, C, D, E determines A. Okay. So if we have B is like the X coordinate, this is the Y coordinate, this is the Z coordinate, and this is the exact time, then that can only determine one object, one atom ID. Right? Does that make sense? So, so I mean, there's a lot of practical. I mean, there's a lot of kind of interpretations of this. So we do it abstractly, but that would be like kind of an interpretation of how we could maybe do like a Pauli exclusion principle or something. But anyways, that was just to show you that we might kind of look at these things. They might have different interpretations. Let's see. We want to stick with something really. We want to stick with kind of easy for the time being. Okay, so so let's just say something like this. Okay, I can just kind of write down these kind of A goes to B, B goes to C, and then DE goes to E. All right, so this right here probably fits some real world situation. All right, but you'd have to kind of like tease it out and kind of give interpretations to what these different things mean. But this. I mean, I'm sure that there's countless examples in the world that have this as the model. Okay, so the issue might be this, would be that, okay, so now let's look at this and let's say that, all right, so we have what's called Armstrong's axiom. So this is F, and it equals this set right here, okay? And then we have Armstrong's axioms, which include the following. So if we wanted to be, now one thing we might want to say, we have 1, 2, 3, 4, 5 attributes, right? Now, are there, if we basically say a functional dependency is X determines Y, right? Then the question would be, is this bounded? Are there an infinite number of functional dependencies we can make over this universal relation, or are they bounded? How many people think that it's infinite? How many people think it's bounded? It's a big number, maybe, but it's bounded. We can't write out an infinite number of these. We can't write out an infinite number of these functional dependency statements. Is that true? When we have 5 attributes. I mean, how many different subsets can we write of this? 32, right? We have 5 of them, so there are 32 distinct subsets. One of them is all of the attributes. Another one is none of the attributes. Another one is like just A, another one's just B, right? So really, if you look at it, we're looking at something like where we would have basically, if we were just going to write out these things, we have to pick like any arbitrary subset here and any arbitrary subset here. So really, what we have is we basically have, we have 2 raised to the 5th times 2 raised to the 5th. Am I right? Those are the total number of distinct functional dependencies we can write over this table here, right? And that means like it's 1024. Right? So we have 1024 distinct functional dependencies we can write over this table here, right? So it's not infinite. In fact, it's just 1024. That's a bound also, because some of those don't make any sense at all because they're just like empty, right? That's not a functional dependency. But otherwise, yeah, those are all the legal functional dependencies we can write over this table here. Does that make sense to people? I hope. Good. All right. Yeah. So that's just kind of giving you like this. It's at least kind of giving you some comfort here that when we compute this closure here, Under the worst case, we'll have 1,024, but we're not going to have anything near that. All right. Now, as we do this, if we want to say compute the closure, so I say I want the closure of this thing. Right? Now, there is Armstrong's axioms, and they're going to basically say here's one of them. It says this: if it says x goes to y, if y is a subset of x. Right? This is the trivial, and we're not going to write the trivialities. These are all the trivial functional dependencies. Right? So there's going to be a ton of those, but that's just we're not going to write them down because they're just trivials. But they may be used. These trivial ones may be used in doing proofs of other ones to kind of get. So that's Armstrong's axiom 1. It's necessary to have actually. 2 is going to be what's called augmentation. So if x goes to y, then xz goes to, oh darn it, yz. I'm sorry if you guys can't see that. You can't see that. If x goes to y, if x functionally determines y, then xz functionally determines yz. Okay? So that's what's called augmentation. If A goes to B, then AC goes to BC. All right. So actually, there we go. AC goes to BC. That's in the closure because we compute that by augmentation. Okay. I mean, I wouldn't. All right. So I mean, very rarely are we actually going to pound out the actual closure instead of function dependency. I just want to give you an idea of kind of what it means for them to be, the closure to be computed. 3. This is the one that's kind of the natural one. If x goes to y and y goes to z, then x goes to z. Okay. Oh, sorry. So this is transitivity. Right? This is the transitivity axiom. And so in other words, if we have A goes to B and B goes to C, that means we have A goes to C is in the closure, right? And if DE, I think I meant to say DE goes to C, but anyways, I'll change that. DE goes to C. Yeah, so basically, A goes to B, B goes to C, and we have the other ones. DE goes to C. Okay, I think transitivity is closed off now. We have a whole bunch of augmentation ones. AC goes to BC. Anyways, it's. I mean, actually, it may not be that hard to write off the non-trivials. But anyways, the key point is this: these Armstrong's these are Armstrong's axioms. So these right here constitute a sound and complete characterization of how to compute closures over a set of functional dependencies. So sound in the sense that each of these is correct. Each of these, you can go back to kind of elementary kind of mathematics or logic, and you can prove the correctness of each of these axioms. But then more importantly, what's showing more power is to say that if a functional dependency cannot be computed using these axioms, then that functional dependency does not hold necessarily from the initial set. Right? So it's complete. That is that if you use these axioms to completion as you're exploring the 1,024 possibilities, that these will always find all the correct answers. What does it mean in practice of Y as a subset? It just means so. The subset here is just is in the naming of the attributes of the relation. So it's not over the relation itself, it's over the attributes of the relation. So the subset here is basically holding between sets of, so like ABC, and so ABC is a subset of ABCD. Therefore, the following functional dependency holds. ABCD determines ABC. And if you think about it, this is really trivial because it's just saying that if I take two tuples and both two tuples agree on A, B, C, and D, then they're also going to agree on A, B, C. Yes, of course. it's a triviality, right? But so I hope that answered that. So this is this is how at least we get to the heart of So typically, what will happen is you start out. Let's just take a really simple example here. I have R and I have A, B, and C. Okay, and I say the following holds over this domain. A goes to B and B goes to C. All right, that's F. That's what we're given, right? So somebody says something like, yeah, the person number, for instance, determines, person number determines such and such. So it might be that the pet ID determines the owner ID, and the owner ID determines the owner's name. So the pet determines the owner ID, and the owner ID determines the owner's name. Therefore, the pet determines the owner name. Right. So that would be just a simple example of that. So when we look at F here, and I say, well, let's compute F plus the closure, then we first use Armstrong's axioms, and we can say something like, well, this time I'm actually going to compute the full closure here. All right. Well, if A goes to B and B goes to C, then using transitivity, A goes to C. Okay. Now let's just go through and let's do all the augmentation. So if A goes to B, then A C goes to B C. If B goes to C, then B A goes to B C. If A goes to C, then A B goes to B C, which is just a variation of that one. A B to B A. I'm sorry, I added A. I did this one wrong. C. So when I was doing the augmentation of it, so B A goes to C A. A B goes to CB. I'll stick it so I do it in standard way. So those are all the ones by augmentation. Then thankfully we don't have any strange kind of transitivity there. And then we have all these kind of just ridiculous ones. A, B, C goes to C. I don't want to write all those out. So basically, but this will terminate, and then we'll have a full closure. Okay. So let's see another question here. So this was part of. So in the earlier example, PID was a part of two different sets. I guess I'll maybe maybe we'll kind of I'll keep that. Let's just kind of stick with this right here. So anyways, I hope that this idea of this transitivity kind of makes sense, and how you start out with somebody making a statement. This is like a human being telling us these are things in the domain. This kind of common sense notions in the domain, and then we can compute the full closure from that. Okay, and then the key takeaway here, of course, is that these Armstrong's axioms are a sound and complete characterization of that. So that's completely captured via Armstrong's axioms. Okay, now we want to talk about. Yes, I'm going to turn off that robot. Okay, sorry about that. So now we want to talk about projections of the set of these functional dependencies over a decomposition. So if I have R prime is A C, okay, so this is like a decomposition. So I let's say that my decomposition is RAC and R double prime is going to be AB. I'm not sure if that's a good decomposition, but it is a decomposition of this original up here. So the idea here then is that what a projection of F, the closure over this, is that you look at all of the functional dependencies that are in the closure and which of them can actually fit over R prime. And in this case here, the only one that can fit is A goes to C, right? A goes to C fits there because A and C are there. B goes to C. These two here, they don't fit. They don't project over R prime here. All right, they don't. There's no. They're not going to find a happy home there. Is there anybody else in this whole thing that doesn't have a B? It just has. No, it doesn't look like. Maybe some of the trivial ones, but basically, what it means that when we're doing the projection of this over this, we're doing the projection of this closure of the original set of functional dependencies. We're doing that projection over these subrelations. Now A goes to B. A goes to B fits in there. Does anybody else? Does B go to A? No, B does not go to A. It doesn't look like anybody else fits in there. So the only functional dependence, if we had our R here and we decompose it into this R and this R here, then if we did that, then the only functional dependencies that would make it through is A goes to C here and A goes to B. All right. And then the question might be, if I take those, if I take these two, and I basically say, because I'll call that F prime, and I do a closure over that, right? So I've projected all these from the closure here over this decomposition here, and I'm going to do a closure of those. Does that closure equal this closure? And it doesn't look like it does, because the closure of A goes to C, A goes to B, yeah, you can do all the augmentation, but you're not going to get anything where it's ever going to say that C goes to B, or B goes to C, rather. We're never going to get B, we're never going to recover B goes to C when we do a closure of this. So they're not equal. So what this means, it means that this decomposition from this down to this is not preserving the dependencies. Okay. So that has to do with like what's called dependency preservation, which we're going to get to. But that's this is just kind of showing that we're just kind of doing it. Now the question might be also is this a lossy or lossless join here? I mean, is this lossless or lossy decomposition? And when we do the rejoin here, we'll do it on A. I have a feeling this is lossy, but anyway, let's just put that off for now. Would all right now is R prime A B and R double prime B C equal? No, it doesn't apply, but we're going to get to more of a definition of that in a bit. But let's just move on here. I just wanted to cover that. Let's do something a little easier now, just so that we because I want to make sure that I don't want to lose people here with that. But I mean, that will. What I told you was true. Maybe just a little bit. The timing was going to be a little bit bad to bring that on. No, so the lossy is much harder. So lossy has to do with something called the Chase algorithm. But what we're going to see in a second here, I just want to back off and be a little more practical because we don't actually have to ever compute. We have an algorithm that can actually do the BCNF for us, which is a lot better. Which I mean, me just kind of like randomly. This maybe was a mistake of mine, but I thought I would illustrate the issue of I thought I would illustrate just the idea of when I took this example here, and then I just said, when I took this example, here it is. One sec. When I took this example here of this right here, and I said, oh, what happens if we just, sorry, wasn't that? It wasn't wrong. When I took this example here, and then I said, oh, let's just randomly kind of pick a decomposition. We never actually, as it turns out, we're never going to do it that way. We're going to have a systematic algorithm which is going to kind of pick our decompositions for us. But I just did this. I thought, oh, well, why not just to kind of show this idea of projection? Why don't I just do that? But since that was just more in the way I was presenting things, it got us a little bit into the weeds in terms of like the lossless and lossy. But maybe we'll come back to this and show that it is lossy or lossless if we get time to do the Chase algorithm. But let's just try to stick with kind of what's a little bit more intuitive here because that's what I'm trying to kind of build up. Okay, so first of all, let's just talk about what the keys of a relation are. So here we have a relation R, A, B, C. Okay. And then I have the following functional dependency. A goes to B, C, okay? Now, the issue would be this, would be that the first question we have is, what is the superkey? And what a superkey, basically K is a superkey if K determines all the attributes of the relation. So in this case, I'll just make the definition if K determines A, B, C, okay? In this particular case here. So a superkey, what a superkey is, if a superkey of a relation is a set of attributes which functionally determine all the attributes of the relation. Okay. I guess the question, I'm going to back off on that. I'm going to back off and answer that one question because I don't want to get lost in the weeds on it. Let's take something a little bit easier here, and then we'll get back to the other one about what was shown or not shown in that earlier example. But I hope that people can follow this much because I want to make sure that I don't lose people here. So we have a relation with A, B, and C are the attributes, and we have the functional dependency A goes to B, C. Now K is a superkey if K determines A, B, C. Okay. Now, if I always ask you, I would say, I give you a relation A, B, C. I say, what is the superkey of A, B, C? And I say, answer me quickly. You have to answer me very, very quickly. We always have it so that all the attributes themselves functionally determine just based on triviality. ABC always determines ABC, right? So if I have another function over here, if I have another table over here which has A, B, C, D, and E, and then I have a set of functional dependencies here, okay, where I specify those, and then I ask you, what is the superkey of S? Then without even looking at these, you can always tell me, oh yeah, A, B, C, D, E is a superkey. Okay, so a trivial superkey, if you will, is always just taking all the attributes of the table. All right. All right. So let's just look at this right here. So is A, B, C a superkey of this relation up here? Yes. Now let's look at, let's try to make something a bit more informative. What are the subsets of this thing? So AB is a subset, BC is a subset, and AC is a subset. Okay. Now, so this is a superkey. Now, if I have A and B, can I determine, if I have A and B, can I determine C? All right. Now, if we didn't have this, then the answer would be no. But we do have this. We have this one functional dependency. And therefore, yes, with A, just A and B, I can determine C. So that's a superkey also. What about with BC? With BC, can I determine A? No. What about with AC? Can I determine B? So, to get the full ABC? Yes. So this is a superkey. This is a superkey. This is a superkey. Now let's kind of go down even further here. We have A. Excuse me. We have A, B, and C here. So C is a subset there. With A, can I determine the full ABC? Yes or no? Well, with A, I can determine B and C, and with A, of course, trivially, I can determine A. So this is also a superkey. And then with B, can I do it? No. With C, can I do it? No. So these are all the superkeys of this relation here, given this functional dependency. Okay, I hope that makes sense. Okay, so that's what the idea of a superkey is. Okay, and then the question is, what is what's called a candidate key? K is a candidate key. K is a candidate key if it is a super key and no proper subset of it is a super key. Okay, so what is the candidate? So is BC a candidate key? It's a super key, but there is a proper subset of A, namely, which is also a super key. Okay, so the only candidate key here is this A. I hope that makes sense to people. Can I make a trivial example here off to the side where we have two candidate keys? Sure. A goes. This right here, if you go and work with this, A goes to BC and C goes to AB. This has two candidate keys, A and C. Okay, so now we got the definition of what a super key is and what a candidate key is. Okay, so that hopefully is moving us along a little bit towards something a little bit more intuitive. Let's see here. All right, let's see here. So when we come back, because I got a little bit lost in the weeds there in some of the examples that I developed here, but hopefully you guys are getting some intuition. We're going to go through and we're going to kind of do a couple of these exercises just so we can kind of identify these candidate keys and these and super keys, of course, which are kind of easy to identify. And then what we're going to do is we're going to show the decomposition algorithm where we take a set of functional dependency statements, and then we're going to actually show an algorithm that does top down, and we actually build the DCNF decomposition. Okay, so just hang with here. I mean, we should get a full picture of it, soon enough. Okay, so let's take a break here and let's get back at 20 after. Yeah, so I'm going to make a phone call here, and let's just pause here. Just put questions in the chat. Okay, so let me just pause. Recording. All right, so let's show. Let's try that. All right, so people wanted to see that they couldn't read the correct definition of a candidate key. I mean, another way of saying candidate key is just a minimal super key. So just think of it this way: that we know what a super key is. And a minimal super key is one where you can't take it. It's still a super key, but you can't take anything away from it. That's the definition of a candidate key. But we're not going to. I don't think we're going to put candidate key to use until next lecture. So just have that kind of in the back of your mind that there's this notion of a candidate key, and there's the more fundamental notion of a super key. All right, because that's the one that's going to be important for BCNF. Remember, BCNF basically says something is in BCNF if for every non-trivial functional dependency, X goes to Y, X is a super key. Okay, that's the definition. So basically, let's deal with let's kind of deal with BCNF for the rest of the lecture here, and let's talk about why it's let's first of all let's show how to get to it, and let's also show why it's good. All right, so let's start out with this example here. So there's our definition of BCNF. Okay, so let me just start out with this right here, and let's just see if the following relations in BCNF. So I have R, A, B, C, D, right? And we have the functional dependency, A goes to B, C, D. And now I'm going to ask you, is this relation here, R, when it's governed just by this functional dependency, is this in BCNF? All right. So then the question is that, all right, so here we have our first functional dependency, A goes to B, C, D, and is A a super key of this relation, given the functional dependencies? Yes. It is, because with A, you can determine A, B, C, D, because A trivially determines A, and then A also determines B, C, and D. Right? So this is in B, C, and F. Right? Now, let's add another functional dependency in here, and let's say that C goes to D. Okay. So now, if this is our F, then I ask you, is this relation here, is this in B, C, and F? All right. Well, the first thing we do, let's be very, let's just be very plotting. Let's be very meticulous about this. So I first go to the first functional dependency. I ask, given these set of functional dependencies, is A a superkey of the relation? Well, the answer is yes. Then I go to this functional dependency here, and I say, all right, now is C a superkey of this relation up here, given all things? From C I get to D, but then I'm stuck. So no, C is not a superkey of this relation. Therefore, this relation is not in B, C, and F because, well, it has an offending or violating functional dependency. Okay? Now, if we want to, we want to do a decomposition of this so that it's in B, C, and F. All right. So we have an offender here. C goes to D. That's an offending relation. So if we basically, here's kind of the algorithm over here. If we have X, one sec here. I just wanna... If X goes to Y is the offending functional dependency, then let's do the following. Let's basically say, so we have R, and R is going to basically be over Z. So Z are all the attributes, right? So in this case, A, B, C, and D. And this X right here corresponds to C, and Y corresponds to D. But more abstractly, what we're going to do is we're going to use this, since this is an offender. This is an offending functional dependency because X is not a superkey of R. What we're going to do is we're going to basically propose the following decomposition into R prime, which is going to wind up being X union Y, and R double prime, which is going to be Z minus Y. Okay. So if we apply this template, so this is kind of how this is how it works. Now, actually, what I would prefer actually do is to invert those and call this double prime and call this single prime, because I like this just kind of the way I like to kind of write it out. Or do I want to do that? No, I can do this one. I'm sorry, everybody. Okay, R prime. So basically, what this means this is that we're going to use this guy here to split this guy into a decomposition. So let me just write over that. So we're going to get two tables that are going to come out of this. One of the tables, the R prime table, is going to wind up being X union Y. And X is in this case C and D. So we're going to get the table CD that comes out of this. And then we're going to get the other table, R double prime, which is everything except for D. All right. So basically it takes the original A, B, C, D, and it minuses off D. Right? Because Z is the A, B, C, D, and then Y here corresponds to D. Right? So then we get A, B, C. Okay. Now, I hope people are following me. All right, so this is this now. What's nice about this is that we go back and we can use theory. That basically what we're guaranteed here is because C is being shared among both this and this right here, that C is being shared, that it is lossless. So this decomposition here, we're not going to like show it right now, but trust that the theory tells us that, and we can develop it if we later on. It's a bit more complicated, but basically, when we do this kind of decomposition here, we're guaranteed that it's going to be lossless. Right? And one of the reasons why we're guaranteed that it's going to be lossless is that we already know that C goes to D, that the C is going to wind up being first of all, C is being shared between these two. And and if we did a natural join between them, well, C is also the left-hand side of this table here. So by definition, when we look at this right here, the way we split it, we know that this is going to be, at least relative to this functional dependency, this is going to wind up being in BCNF. But let's just look at this. Let's just consider this a bit more. Now, what the theory tells us also is that we have to look at F here, and we have to just consider the closure of F. All right. Consider the closure of F, and then project that over the subrelations here. And so they're going to have like this, the F that's going to be down here is basically going to be like the closure of this F projected over this. So it's going to wind up actually just being C goes to D, right? That's probably the only one, because in the whole closure here, we're not going to wind up getting C goes to anything else. So we're going to have like down here, we're going to have the functional dependencies that are projected from we're going to do the closure of this, and then we're going to project it over this, and we're going to wind up getting that. I hope that makes sense to people. So in other words, it makes no sense to bring down A goes to C down here because there's no A, right? So, but mechanically, what you're doing is you're doing the projection here, and then, I'm sorry, you're doing the closure here, and then you're taking that closure result and you're projecting over this. But we can look at it, and it's pretty obvious to see the only one that's going to survive is C goes to D, all right? And likewise here, we're going to wind up having a set of functional dependencies. A goes to B, and A goes to C, and that I think, and then then A goes to B, C, etc. All that. But basically, this is sufficient to look at the projection of just of these two down here. Does that make sense? I hope. Okay, now what we do is we re-instantiate the whole problem, and we ask ourselves, for this little baby here, this R prime, is this in BCNF? And we only have to check it relative to the set of functional dependencies. All right, is C a superkey of this R prime? Yes, good. I see. Well, I got that as a direct message, so I guess probably didn't see it, but somebody, yeah. So okay, so this one's done. So we're as far as BCNF goes, we're done here. That's in BCNF. Now we go over here. Is this functional dependency A goes to B? Does this right is A a superkey of this of R double prime? Yes. Good. I see a bunch of yeses. Is A goes to C? Is A a super? Yes. Okay. So this too is in BCNF. All right. So what we've done here is we've gone and we've taken like from the theory told us. First of all, what the theory is telling us, if you remember that one slide, is it says we're given like a universal relation, and we're given a set of functional dependencies that govern it, and we want to move everything in this inner circle here called BCNF. Otherwise there's these other. So we start out here, and then we drive toward BCNF. We want to get to BCNF, right? Now it looks like we've done it. We've done a decomposition, and I'm telling you, in part, just trust me here, that because of the way we're doing the decomposition here, the kind of binary decomposition, we can guarantee that it's lossless, so we're not losing any information. Now what we've done is we've actually we've gone and we've done the decomposition, and we've projected down all the relevant functional dependencies, and then what we wind up doing is we wind up determining each of these is indeed in this BCNF, which is good. We're there now. And what's even better, if I call this F prime and I call this F double prime, right? And then I'll call this F right here. What we'll also see here is that F under closure equals F prime under closure union F double prime under closure. Okay. And so what this, so in other words, what this is basically saying is if I do the closure, because A goes to B, A goes to C, and C goes to D, then in the closure, so what this is going to have is this is going to have A goes to B, A goes to C inside of its closure, but it's not going to have A goes to D inside of its closure. Sorry, I need to actually do the closure over. I think actually this is, I made a mistake here. It was more that is what I want to do. So what I do is I project, I have C goes to D, I have A goes to B, A goes to C,
And under that closure, I'll then recapture that A goes to D. Okay. So and that'll make it so that it's equal to the original closure. I just put the pluses here a little bit to it was kind of obvious, kind of dumb. I mean, you just need to union all the functional dependencies at that, across the decomposition, and then do a closure of those. And if that equals the original set under its closure, then you know that it's dependency preserving. Okay. Now, I hope this is making some sense to people. All right. So what's the big deal about this? Why do we even really care so much about this? Well, we looked at those anomalies, those insertion and deletion anomalies, and those are now under BCNF. We got rid of those. We got those simple ones. We got rid of those, and so we don't have this kind of redundancy and weirdness in the database. So it's kind of got nice properties. And we've kind of translated everything down into, so we've essentially done the decomposition. We could do the same decomposition with the original example that we worked just by using this simple kind of decomposition rule. Right? So I hope that this is a top-down algorithm. But now, why is it important? Why is it really useful in any way? The reason why it's useful, actually, this is kind of the thing that I don't think textbooks mention this so much. I don't think our textbook mentions this, but it's something to keep in mind. If you push everything down to BCNF, especially if you're preserving all the dependencies and everything like that, what this corresponds to then, so now we're going to define these tables here. That means that basically we take the, we take the candidate key, but that's not so relevant here. But when we declare the SQL here, we declare the SQL with a primary key here. C winds up being the primary key. A winds up being the primary key here. What winds up happening then is that when you push things down to BCNF, then you can have primary keys and unique are the constraints that can preserve all that can enforce the dependencies at the leaves, and those are just basically done through SQL declarations. So basically, there's a correspondence between BCNF and SQL primary key and uniqueness declarations. Let me try to be a little clearer here about that. So I ask you guys the following question. Oh, here we are. I got a nice big direct message here. Let me see. So what we're basically doing is check to see if there's a primary key for 677. Kind of. Why don't I just maybe this will hopefully this will kind of clear things up a little bit here. Let me just this will also be a good test to see kind of where you guys are at here. Okay, A goes to B, or A B C D. A determines B C D, and B determines A. All right. So I asked you now, is this in BCNF? Given these are the functional dependencies, this is the table. Is this in BCNF? Good. Yes, good. You guys are catching on then. Okay, and that's because A is a super key, right? So this one's fine. This was checked off. And then D goes to A. All right. With D, can I determine A, B, C, D? Well, I can determine D, I can determine A, and with that, I can determine B and C. Yes. So this also checks off in terms of being a super key. The left-hand side being a super key. So this is in BCNF. Now, how do we declare this in SQL? All right. It's a create table. A, B, C, D. And then we say primary key, A, unique, D. Okay? More or less, right? I mean, the syntax is different, of course, but I'm not even giving these things types. But the issue is this, is that there's a correspondence between, so if you have multiple candidate keys, right? You have multiple candidate keys in the, because this is kind of a generalized case of the BCNF where you have multiple candidate keys. If you have multiple candidate keys, you get to pick one, a distinguished one, like in this case A, and make that the primary key, and all the other ones can wind up being unique. All right, so unique constraints. So let's say, for instance, this is kind of stupid, but let's say that C goes to A. Now, is this in B, C, and F? Yes, of course, yes, it is. So in this case, it would be unique C as well. So the point is that there's a direct correspondence between something being in B, C, and F, and then your ability to declare it in SQL. Okay. All right. So that's kind of a nice property. All right. So that means that basically if we're given kind of, if we're going to model something with like we have this full universal relation, we want to break it into tables. What we want to do is want to push it down so that we have each of the different tables is in B, C, and F. And if we're lucky, all the dependencies have a happy home in one of the tables. So therefore, we can preserve all the dependencies. Now, the fact is that you can't always do that. So let's show a very, very trivial example of something where things break down. Okay, so if I say that A, B goes to C, and C goes to B. Now, does this happen in the real world? Sure. It's like saying, I think we had an example of this already, in fact. Well, it's like saying that let's say that, for instance, we had this thing. The A was address, and then B was city. So the street address and the city determine the zip code or the postal code, right? But then it may be that the postal code determines the city, right? People see that? Okay, so that's possible. Okay, so the question would be this: is if I have R, these are the functional dependencies I have. A, B goes to C, and C goes to B. Now, if I have A, R, A, B, C, the question is this in B, C, and F? Given these functional dependencies. That's right. Which is the offending one? It's this one right here, right? Because C is not a superkey. That's right. Okay. So let's then say, fine, not a problem. Let's just bust it down into, let's bust this thing down let's do a decomposition then. So this is the offender, CB is the offender. So that means that the decomposition would be R prime, and then it would be CB, right? And then R double prime, AC. Okay, we do the closure of this and we project it. I'm sorry, I'm being kind of dumb. CB. Yeah. So we do the projection of all this over here, and then we find that C goes to B has a happy home in this table here. I do the projection of A, B goes to C over this right here. You can't, unfortunately, this dependency here just cannot find a happy home either in this table or in this table. So it's lost, it doesn't get represented. So we can do a BCNF decomposition, but now we're losing this functional dependency. Okay. So often then the issue is like, well, that's kind of unfortunate. Somebody might say, that for us, we feel like actually that we feel as if that this is actually a more important one we want to be able to represent. This zip going to city, we don't really care that much about this one. So we're saying, well, we know this is not in BCNF, but then strictly speaking, we'd like to just stop at this point here because we really want to preserve this dependency here. We really don't want to lose this dependency. It's an important. It's kind of more important to us than the zip code of the city. So and this is of course, I mean, there's countless examples where this can apply to the real world, or where these things happen. So a lot of times when you actually wind up having something like this, you wind up saying that this is kind of a more important. We want to maintain this dependency. We want to keep that. Okay, so BCNF is like kind of like, actually, I'll draw you out like what ultimately here. This is the ultimate picture we're going to get. We're going to have BCNF, and then we're going to have something called fourth normal form, which we're going to cover next lecture. This is actually really where we want to get to, is fourth normal form. But then there's something called third normal form, which tolerates this, but it's still good. It's still actually much better than something like second normal form, or God forbid that you don't make it to even first normal form. So we always assume that we're in first normal form to start out with, where in first normal form is simply we're inside of first normal form if all of the values are atomic on tuples. And then what we do is we want to drive through. What we were wanting to do before is get to here, but sometimes we'll accept just to get to here, to get into this weaker third normal form, because of the importance of keeping around certain dependencies, right? So I've shown you that if we drive all the way to BCNF, we can lose a dependency. We're losing this dependency. So we want to back off a little bit, and we want to just look at something that's a bit weaker than BCNF, but something that will always preserve our dependency. So what's nice about 3NF is that it will always preserve our dependencies. So we can always push things into 3NF, and then we will always preserve all the dependencies, okay? But it's not as good as BCNF, but sometimes we want it rather than BCNF because we want to keep these. We want these types of dependencies to be represented. I mean, in principle, you could represent this, you could break things down to this level here, and then have extra code inside your system that will actually enforce this dependency. But that's kind of a junky way of doing it. Okay. So let's look then at this. So we've covered BCNF and how to get to it, this top-down algorithm. Now let's look at 3NF and see kind of what its definition is. Okay, so now actually we can look at this issue of the candidate key. This is kind of an important thing. All right. If an attribute is a member of a candidate key, an attribute that is a member of a primary key is prime. Okay, just a definition. So all right. Now when we look at what we look at when we look at all right, so listen here. For a set of functional dependencies, okay, for a given relation and a set of functional dependencies where if X goes to A, and I'll get to this in a second. If X goes to A, then X is a superkey or A is prime. Okay, so let's I want to just get back to our earlier example so we can build. All right, so we look at this one right here. Okay, so what are the, okay, first of all, let's just take this away for a second here. Let's just start here. We have ABC here. All right, so what are the super keys of this relation here? So ABC is of course a super key, and then is AC a super key? Yeah. And is AB a super key? Yes. And what about BC? No, it does not appear that BC is a super key. Right, so that's a super key, right? AC is a super key because with A and C we can get B, and with A and B we can get C. Okay, so those are both super keys here. Now, is A is not, right? Because with A you can't get them all. B is not, and C is not. So basically the question is, what are the candidate keys of this right here? What are the candidate keys of RABC? No, they're AC and AB. Okay. So all of these are prime because they're all a member of a candidate key, right? So is A prime? Yes, A is prime because A is a member of a candidate key. Is B prime? Yes, B is prime because it's a member of a candidate key. Is C prime? Yes, C is prime because C is a member of a candidate key. Okay. Now this business here. So if A, okay, an attribute is, okay, this is already prime. Okay, so let's just do the full definition here. It's 3NF. Okay. A relation R is in 3NF if for every X goes to, let's, and I'll make it like a script A that represent, that's just a single attribute. It's not A, but it's a single attribute. If for every X goes to in the canonical, canonical, in the canonical form of F. Okay, this is where it gets a little, maybe it gets a little tricky. So I can always put F, a set of function dependency, into a canonical form where we only have one attribute on the right hand side. So look, think of it this way: if I have A, B goes to C, D, E, and I have C, D goes to G, and I have G goes to H, I, this is equivalent to A, B goes to C, A, B goes to D, A, B goes to E, C, D goes to G, and G goes to H, and G goes to I. So I can always take a set of functional dependencies and I can convert them into their canonical form, into this canonical form where these are equivalent, F and F prime. I can always transform them into an equivalent canonical form where we only have one attribute on the right-hand side. Okay, and you can use Armstrong's accent to show that's a legal conversion, an equivalent the dependency preserving transformation of the original set to a new set that's under this canonical form. Okay, so when we talk about 3NF, we're always talking about relative to a set of functional dependencies in the canonical form. So for every X goes to some A, either X is a super key or A is prime. Okay, those are the two conditions. All right, so based on that, then what we get is when we look at this kind of simplest possible example, we can show this is actually in 3NF, right? So R, A, B, C, where we have A, B goes to C and C goes to B, right? Well, we've already determined each of these are, all right, so is this in canonical form? Yes, this is already in canonical form because we only have one attribute on the right-hand side, right? Is AB a super key? Yes, AB is a super key of this relation. Is C a super key of this relation? No, but B is prime. Therefore, this is in 3NF. Okay. So that's just, so it might feel like kind of like weird, like, well, what does that really, well, you know, if you say so, like, well, I mean, sure, yeah, I mean, what's this prime stuff? Let's look at let's try to look at an example here of something that would be, would not be in 3NF, just to kind of maybe build a little bit of intuition. I have R and I have AB goes to C. I'll say CD, why not? So R, A, B, C, D. AB goes to that, and then, Michael, sorry, screwing everything up here. Now I need new fresh paper. I'm going through a lot of paper here. Ah, here we go. Okay, so now R is A, B, C, D. Okay. And then we have, yeah, let me start off with a trivial example, or a simpler example, the ones that has transitivity. A, B goes to C, and C goes to D. Is this in 3NF? Let's just walk through it. Good. I'm glad to see that. Okay. Somebody, yeah, they see that it's not. This is not in 3NF. Let's walk through why it's not in 3NF. First function dependency. AB goes to C. Is AB a superkey of this? With AB, I can get C. With AB, I can get D. With AB, I can get A, B, C, D. Okay, so this no problem with this rule here. No problem with that function dependency. Oh, somebody else. Yeah. All right. A relation here. Let's maybe fix this up here so we get the definition right. Okay, a relation R is in 3NF if for every X goes to A in the canonical form of F. So you know, F is the for a relation R governed by F. Relation R governed by F is in 3NF if for every X goes to a single attribute in the canonical form of F, because we can form the canonical form of F, then either X is a superkey or the A is prime. Does that help, I hope? Okay, good. So that's, you can like, it's a little bit clunky, but this I think is your definition. This is 3NF. 3NF. Yeah. All right. And then I ask, based on that, is this in 3NF? This is a superkey. That's fine. D is D prime. Is D the part of any candidate key? Is D the part of any minimal superkey? Doesn't look like it. D is not prime. So this is the offending, that's the offending functional dependency. So this is not in 3NF because it has this transitivity in there. Take another example. A goes to B. I mean, you can sit there and say, I mean, I can make this more elementary. You'd say, oh, I have no idea what is this ridiculousness that Michael's doing. All right, let's back off and ask a simpler question. What are the candidate, given this right here, what are the candidate keys of that? AB is the only candidate key, right? That's the only candidate key. I mean, what are the super keys? I mean, it's like, you know, it's like always if somebody says, give me a super key of this. Somebody puts a gun to your head and says, I want a super key of this relation. You always just spit back all the attributes of the relation. That will always give you that, right? And then you can go and you can start playing around with taking subsets of that and seeing. And I'm telling you right now, AB is the only subset of the AB is a superkey, and it's the only superkey where there is no subset of it, which is still a superkey. All right. ABC is a superkey, ABD is a superkey, but they always have AB as a subset, so they're not candidate keys. All right. So therefore, the only candidate key is this guy right here under these functional dependencies. The only candidate key is AB. Therefore, D is not prime, right? Because it has to be a member of a candidate key to be prime. A is prime and B is prime. C is not prime and D is not prime. So when we do the test here, D is not prime, and therefore this is offending and failing both on the C is not being a superkey and also the D not being prime. All right, so this is not in 3NF. Just in time we have here, let's just do another one here. AB goes to CD and B goes to C. Is this in 3NF? This comes up a lot in the real world. This one, is this one here in 3NF? Is AB a superkey? All right, so these are done. Good. So it is not. And the reason why it's not is because C is not prime. Okay. All right. So what we're going to show next time is we're going to show a way. So we've already shown a way to get, and we'll kind of in the time we have, we're going to kind of play around with these a bit more. So we get, we have 2 more hours to deal with this. We're going to kind of try to get a bit more intuition about the decomposition algorithm, and you'll do that in recitation as well. But what we're going to show next time is we're going to show a way in which, a very systematic way in which we can actually do the 3NF. We can build up from bottom up. We can build up the 3NF decomposition of the tables. And the 3NF actually, a lot of times, is what you're looking for a little bit more in the real world, is looking for 3NF decomposition. So a lot of times there'll be a correspondence. A lot of times you'll build the 3NF decomposition, and you'll look at it and you'll say, lo and behold, this is in BCNF. Great, it's in BCNF. But what's nice about the 3NF algorithm is that you're never going to lose a dependency. All the dependencies you specify are going to make it into the model. All right, and so that's really kind of a nice property of 3NF, that you won't lose dependencies. So we're going to do that, and then we're going to look at something called multi-value dependencies, and then we're going to look at this 4NF. And if we have time, which I don't think we will, we're going to look at what's called the chase algorithm to kind of arbitrarily determine whether or not things are lossless or lossy or lossless, which would correspond to one of the directions I took it earlier last hour. So yeah, so I hope this is starting to make some sense. It is good stuff to know, and it comes up, and we'll do some exercises where we show that this has relevance to design. So okay. All right, so if there's any questions, ask them. Otherwise, I will pause or stop recording and see you all on Thursday. So I'll stop recording.